The force of gravity is a central fact of everyday life. It influences everything around us. It steers how things move. It shapes their structure. If you get out of bed or throw a ball or build a house, you have to deal with gravity. But of course, that's not all that gravity is about. Last time, we looked at 3 discoveries of Galileo Galilei: the principle of inertia, the law of free fall, and the principle of relativity. These tell us about motion and gravity for objects here on Earth. But Galileo also had other things on his mind, not just the paths of projectiles, but how the whole universe is arranged and how we fit into it. Galileo invented the astronomical telescope, and with it he made discoveries that changed our understanding of the universe. That revolution in the heavens is part of the story of gravity too, and we'll approach that story through the eyes of Galileo's great contemporary, Johannes Kepler, the great German mathematician, physicist, and astronomer. Now, Kepler did not start out as a famous scientist. He started out as a school teacher, but he had a number of qualities that suited him for the discoveries that lay ahead. First, he was a master of mathematics. He was one of the great geometers of his time. He knew all the mathematical tools, and he invented quite a few of his own. Second, Kepler was a man of profound faith. I do not mean religious faith, although Kepler was a deeply religious man. I mean an intellectual faith, a faith in his own insight, a faith in the mathematical beauty of the world. It was faith that let him persevere through all kinds of difficulties, working on heartbreaking scientific problems that might take years to solve, dealing with his own difficult personal life. He was often in trouble, he was often in debt, and he was often in a court of law. Finally, Kepler had one more vital quality. He could change his mind. If he had an idea, he might labor night and day to make the idea work, but in the end, if the idea did not work, he could abandon it and try something else. It sounds simple, but it is an essential quality for a scientific pioneer. Now, in his university days, Kepler studied mathematics and astronomy, and almost at once he became convinced of the radical Copernican theory of the universe. Now, we've mentioned that before, but I think it requires a little explanation. For most of history up to Kepler's day, almost everyone believed that the Earth lay at the center of the universe. That's the way it seems. We stand on the Earth, which seems to be at rest, and the heavens seem to move around us. The sun and moon and stars and planets are rising and setting and shifting around. So this naive idea was turned into a sophisticated mathematical system by ancient thinkers in the Mediterranean world, most notably Claudius Ptolemy. Now, in Ptolemy's system, a planet moved on a small circle called an epicycle, and the epicycle itself moved on a big circle called a deferent, all moving around the Earth. And the combination of these motions more or less explained how that planet moves in the sky. But then, in the early 1500s, a Polish cleric named Nicolaus Copernicus proposed a radical theory. Copernicus said that the Earth is not at rest. The sun is at rest. The Earth is actually a planet that goes around the sun with the other planets. It moves along its orbit, and it also rotates on its axis. Now, the moon does go around the Earth, but the planets all go around the sun. According to Copernicus, the complicated motions of the other planets in our sky are due both to their own motion in space and also the way our own point of view moves along with the Earth. Copernicus fully explained his theory in his great book on the revolutions of the heavenly spheres, which was published in 1543. And that's the theory that 50 years later caught young Johannes Kepler's attention. So why was Kepler attracted to the ideas of Copernicus? Well, for one thing, he thought it was a more elegant way to explain the motions of the heavens. He also had some rather strange-sounding geometrical ideas about the Copernican system. Kepler believed that the sizes of the planetary orbits were related somehow to the properties of geometric solids. This is a half-crazy mystical idea, and Kepler would later abandon it. But he worked it out with great mathematical ingenuity, and he published it in a book titled Mysterium Cosmographicum, or Cosmographical Mysteries. And that book brought Kepler to the attention of a prospective employer, the greatest observational astronomer of his day, Tycho Brahe. Now, Tycho was a Danish nobleman who became interested in astronomy. And he became very dissatisfied with the state of astronomical theories in his day. They just weren't very accurate. At least they weren't very accurate by Tycho's exacting standards. So consider the motion of the planet Mars in the sky. Both Ptolemy's theory and Copernicus's theory make predictions about those motions. They say that on such and such a day, you'll find Mars located in such and such a place in the sky, near these stars or those stars. But at times, those predictions of the motions of Mars might be off by as much as 5 degrees. The errors in Ptolemy and Copernicus are roughly opposite, but both make errors of about the same size. All right, how big is 5 degrees? Well, here's an old astronomer's trick. Your little finger, held at arm's length, is about 1 degree. If you hold 3 fingers side by side at arm's length, that's about 5 degrees. 5 degrees does not sound like much. And that's why Ptolemy was accepted for 1,500 years. But if you are interested in absolute precision, like Tycho was, 5 degrees is too much. It's kind of frustrating. Luckily, Tycho had a wealthy patron, the King of Denmark. The king granted him an island and the money to build a great observatory there, Uraniborg, the first great scientific research laboratory. There were observatories, workshops, great instruments for measuring the positions of the stars and planets with extreme and unprecedented precision. Of course, there were no telescopes. Telescopes were still a generation in the future. And for 20 years, Tycho and his assistants, the Tychonites, created an astronomical database, a record of observations unequaled to that time, both in completeness and in accuracy. How accurate? Well, remember, a little finger at arm's length is about 1 degree. The diameter of the moon in the sky is about half as much, about half a degree. The typical accuracy of Tycho's observations is about 1/30th of a degree. Well, the old king finally dies, and the new king was not so inclined to spend quite so much money on Tycho's work. So Tycho takes his observations and his instruments, and he leaves. And eventually, he settles in Prague. The Holy Roman Emperor names him imperial mathematician. So he sets up court, and he hires some new Tychonites, including that up-and-comer Johannes Kepler. Now, Tycho does not really agree with Kepler's Copernican ideas. He believes, like Ptolemy believed, that the Earth is at rest in the center of the cosmos. But he knows that his observations could be the basis for a new and more accurate astronomy. And Kepler is the man with the creativity and the mathematical skill to forge that new theory. So Tycho assigns to Kepler the problem of explaining the motions of Mars. And just as Kepler starts to work on it, Tycho himself dies. Kepler is named his successor as imperial mathematician, and Kepler takes custody of all of Tycho's observational records, which causes a long-running dispute with Tycho's family about inheritance and even more lawsuits. But Kepler continues to work on the problem of Mars for several years. Now, Kepler has two things going for him. First, absolute confidence in Tycho's data. And second, he has a glimpse of a new idea, a way of thinking about Copernicus. It's really an insight about physics. You see, the actual Copernican theory is not quite as simple as we've described. What is the shape of the orbit of a planet? Well, it's a circle in Copernicus's theory, but that circle is not centered on the sun. To make the theory more accurate, Copernicus has to shift the orbits a little. And so Kepler asks, why should a planet move around a point in empty space? The path of a planet, he says, is not just an arbitrary curve, however mathematically beautiful. The planet moves through space the way it does for some physical cause. And that physical cause, Kepler says, must lie in the sun. The sun must govern the laws of planetary motion. This is a million miles away from the mystical, mathematical nonsense of the mysterium. And this is the idea that will be Kepler's compass through the wilderness. And for the next 8 years, Kepler works on the problem of the orbit of Mars. He calls it his war on Mars. And he asks two questions. What is the shape of that orbit? And what law governs the planet's motion around its orbit? This is not very easy. Remember, all of our observations are made from the Earth, and the Earth is itself moving. We have to take that into account. So how do you figure out how the Earth moves? And here's Kepler's clever answer. We know that Mars takes 687 days to go around the sun. That's not quite 2 years. So every 687 days, Mars is at the same point in space. So Kepler can look at Tycho's records. He can find observations of Mars that are 687 days apart. He can do this. He has 20 years of complete data about the positions of the planets. And so each observation of Mars can be mathematically turned into an observation of the Earth from that point in space. You see, it often happens that a great discovery depends on an insight into the way we ourselves see the world. And in Kepler's work, the key is to figure out how our own point of view on the Earth is moving. All right, so once Kepler determines the shape of the Earth's orbit, he can go back and determine how Mars must be moving. So what is the shape of the orbit? Well, an off-center circle almost works, but it is off by about 1/8 of a degree. Tycho's observations should be accurate to 1/30th of a degree. Kepler believes in the accuracy of Tycho's data. He concludes the orbits cannot be circles. This whole process is unbelievably complicated. All the math is done by hand. We have almost 1,000 pages of Kepler's handwritten calculations. And in fact, it's hard to recognize the right answer when you find it. In fact, Kepler originally found the correct answer for the shape of Mars's orbit in what we would now call polar coordinates. And he didn't understand it, and he rejected it. And then later, he rediscovered it. He found it again. And there are other complications. Remember, the orbits do not really lie in one plane. The plane of Mars's orbit is tilted by almost 2 degrees to the plane of Earth's orbit. That makes the calculations even more challenging. And the number of possible curves for the orbit is infinite. But Kepler perseveres. And he solves the problem not just for Mars, but for all the planets. In the year 1609, Galileo is turning his new telescope onto the heavens. It's 66 years after Copernicus published his book. And in that year, Kepler announces his first 2 laws of planetary motion. So, Law number one is called the law of ellipses. The orbit of each planet is an ellipse with the sun at one focus. An ellipse is a kind of squash circle. And a circle it can be thought of as a special type of ellipse. And most planetary orbits are ellipses that are not too far from being circles. Now, if you want to measure the size of an ellipse, it's natural to think of the major axis, the long axis of the ellipse. And the semi-major axis is half of the long axis. And it's a length that's generally denoted by the letter A. And this is, roughly speaking, the average distance of the planet from the sun. And if you have a circular orbit, A is actually equal to the radius of the orbit exactly. Next is the law of equal areas. A line from the sun to the planet sweeps out equal areas in equal times. So when the planet is closer to the sun, it moves faster in its orbit. When the planet is farther from the sun, it moves slower in its orbit, so that the kind of pie piece-shaped wedge that is traced out has equal areas in equal times. So for a circular orbit, the speed would be constant. Now notice something. In both of these laws, the planet's path and the planet's motion is connected to the sun, not to an arbitrary point in space. Up until Kepler's discovery, almost everyone, including the youthful Kepler, believed that planets move through space because they have a motivating force inside them, a soul. In other words, the thing that determines the planet's path lies within the planet itself. But Kepler has a different idea. He says the force that steers the planet comes from the body of the sun. That's why the planet orbits the sun, and not just some arbitrary point in space. So what is the nature of the force? Kepler does not know. He compares it to light. He says its strength diminishes with distance. And he compares it to magnetism, which is another invisible force between objects. William Gilbert in England has just published an important treatise about magnets in the year 1600. Now, Kepler may not understand what the steering force is, but he understands that it is a physical influence acting from a real object, the sun. And he also thinks that the same kind of force acting from the Earth might steer the moon in its orbit around the Earth. So, armed with these two fantastic laws, Kepler embarks upon a long and arduous process, a process to make new tables of planetary positions based on the theory, a task requiring 20 years of labor. But his theory is still incomplete, and Kepler knows it. So, what's missing? Kepler knows the shape of each planet's orbit. He knows how each planet moves on different parts of its own orbit. But he does not know how the orbits are related to each other. And they ought to be related. They are governed by the same physical cause, the sun. Now, Kepler does notice a qualitative trend. Planets with smaller orbits, like Mercury and Venus, move more quickly. The length of their orbital period, the time for one orbit, the length of the year for that planet, is short. Planets with larger orbits, like Jupiter and Saturn, move more slowly. The length of their orbital period is much longer. So, in other words, there seems to be a mathematical relationship between the size of the orbit and the orbital period, which we could call p. But the exact relationship is hard to pin down. It's not true that a planet twice as far from the sun takes twice as long to make one revolution. It actually takes more than twice as long. So let's draw a graph. On the horizontal axis of our graph, we'll have the semi-major axis A of each planet's orbit. And on the vertical axis, we'll put the orbital period p of the planet. And each planet is a dot on our graph. And we can see that the dots lie on a curve that sweeps upward. But what is the shape of that curve? Kepler wrestles with the problem for years. And then in 1614, he hears about a new discovery. The Scottish mathematician John Napier has invented a new mathematical tool: logarithms. Now, logarithms are amazing things. Each number has a logarithm, which is another number that's related to it. And once you calculate the logarithms for numbers, all other calculations are simplified. Multiplication and division are reduced to addition and subtraction for logarithms. Now, Napier figured this out and published tables of logarithms in a book. And Kepler realized that logarithms would simplify his astronomical calculations. He became an instant logarithm enthusiast. And it appears that logarithms led him to his next breakthrough. So let's go back to our graph. But this time, let's plot the logarithms of the semi-major axis and the orbital period. When we do this, all of the dots that represent the planets, all of the dots lie on a straight line. And the slope of that straight line is exactly 3/2. From this discovery, Kepler can work out the relationship between the original numbers, the original semi-major axis and orbital period. And in 1618, he publishes his discovery, a third law of planetary motion, the harmonic law, because it expresses a kind of a musical harmony between the planets. It goes like this: the cube of the semi-major axis of a planet's orbit is proportional to the square of its orbital period. In symbols, that's a cubed equals k times p squared, where k is a constant that has the same value for all of the planets. Now, this looks quite obscure. So let's try it out. First of all, what is the constant k that appears in the law? Well, that depends on the units of measurement that we use to measure A, the semi-major axis, and P, the orbital period. So here's a convenient choice that makes things easy. If we measure A in astronomical units, or AU, then everything's easy, because an AU is the radius of the Earth's orbit. Earth's orbit has its semi-major axis of 1 AU. So all of our distance measurements will be based on the Earth's orbit. And we'll measure our time, or orbital period P, also based on the Earth's orbit. We'll measure it in years, the orbital period of the Earth. So A is in AU, P is in years. Thus, for the Earth, K, the value of K, equals A cubed divided by P squared, which is 1 divided by 1. K has a value of 1. If we measure AUs for distance and years for time, then K has a numerical value of 1, and that value will be the same for all of the planets. Now, this means we can use this value to do calculations about the planets. For example, Jupiter's orbit around the Sun has a semi-major axis, A equals 5.2 astronomical units. And we can use Kepler's harmonic law to figure out its orbital period. A little algebra will show that P is equal to the square root of A cubed divided by K. This is a handy formula. And so if A is 5.2, we find, and K is 1, of course, we find that P is 11.9. And that's correct. Jupiter completes its orbit in 11.9 Earth years. 1 Jupiter year equals about 12 Earth years. The harmonic law applies to all the planets. It shows that they are all steered in their orbits by the same force. It's a force that Kepler realizes must lie in the Sun. And now comes something extra. When Galileo turned his telescope to the heavens, he made many surprising discoveries. And one of these was the discovery that just as the Earth has a single moon that orbits it, some other planets have moons of their own. In fact, the planet Jupiter has 4 moons, bright moons that Galileo observed. We now know more moons, but 4 of them that Galileo saw. And those 4 moons form a little planetary system of their own, with Jupiter at the center. And that's not just a charming analogy between the system of moons and the system of planets, because in the years after Galileo and Kepler in the 17th century, astronomers found that the moons of Jupiter follow Kepler's laws. Their orbits are ellipses, near perfect circles in their case. A line from Jupiter to each moon sweeps out equal areas in equal times. And the orbits are related to each other by Kepler's harmonic law. A cubed equals k times p squared. But in the case of Jupiter's moons, the value of k is not the same as for the solar system. It's much smaller for Jupiter and its moons than it is for the planets that go around the sun. Kepler's laws, it turns out, are not just about planets and moons. Anything that flies freely through the solar system actually follows those laws. Consider the Voyager 1 spacecraft, which was launched from Earth in 1977 and sent on its way toward the planet Jupiter. During its long 18-month journey, Voyager was effectively a planet of its own. The curved trajectory that it followed was a section of an ellipse, Voyager's own elliptical orbit around the sun. A line drawn from the sun to the spacecraft swept out equal areas in equal times. And even though Voyager did not complete an entire orbit before reaching Jupiter, if it had, that orbit would follow the harmonic law as the same harmonic law as the other planets. That is to say that p squared would be proportional to a cubed. Why? Because Voyager was being guided by the same force that guides the planets. The same force that Kepler guessed holds the Earth's moon in its orbit and steers the moons of Jupiter. So what is that force? Kepler never figures it out. He continues to think that it might be something mysterious, like magnetism. But it is Isaac Newton, half a century after Kepler and Galileo, who realizes the astonishing truth. The force that steers the planets and the moons is actually the most familiar force of all. It's gravity, the same force that makes the apple fall from the tree. With this tremendous discovery, Newton is able to finish the revolution in the heavens that Kepler began. So, Newton and gravity, that's next time. I'll see you then.